There's a wound on the face of the sun the size of 60 Earths, and it's pointing straight at us like the barrel of a cosmic weapon. You didn't feel it open. You didn't see any alert flash across your screen. But while you were going about your day, scrolling through your phone, planning your week, something tore through the sun's atmosphere in a way we rarely see at this stage of the solar cycle. A breach in the magnetic structure that normally contains the fury of our star. And from that opening, a river of charged particles is racing toward Earth at over 1 million miles per hour, carrying energy that could reach down and touch every piece of technology you depend on to live your modern life. This isn't some distant cosmic event that scientists debate in journals. This is happening right now, and the consequences are already unfolding in ways most people will never notice until something stops working. Stay with me for the next several minutes because we're going to explore exactly what's happening 93 million miles away, why this particular opening in the sun has caught scientific attention, what it actually means when we say a hole has opened in our star, and most importantly, whether you should be worried or simply aware that we live on a planet orbiting something far more dynamic and unpredictable than the steady yellow circle we see in the sky each morning. You see, we've built a civilization on the assumption that the sun is stable, predictable, safe. Your alarm goes off because satellites orbiting overhead keep precise time. Your morning commute depends on GPS navigation that requires those same satellites to function flawlessly. The food in your refrigerator stays cold because power grids spanning entire continents deliver electricity without interruption. Your ability to call someone across the world, to access your bank account, to watch this video right now, all of it hangs by an invisible thread that stretches between Earth and the sun. And that thread is under stress right now in ways that most people don't understand and won't recognize until the systems they take for granted start behaving strangely. The sun is not a lamp that simply provides light and warmth. It's an active, churning ball of plasma with a magnetic personality that shifts and changes, and occasionally it does something that reminds us we're living in its domain, subject to its moods, vulnerable to its power. Before we go deeper into what's actually happening up there, I need you to do something for me. Hit that like button on this video because what we're discussing is information that genuinely matters for anyone living in a technological civilization. Drop a comment telling me where you're watching from because I want to understand how many different parts of the world are represented here, all of us living under the same star, all of us equally exposed when it decides to flex its power. And if you want to stay informed about the kind of cosmic events that can actually reach down and affect your daily life, subscribe to this channel because understanding what happens 93 million miles away has stopped being optional for anyone who depends on electricity and satellites. Now let me explain what a coronal hole actually is, and why this one is particularly significant at this stage of the solar cycle. Imagine the sun wrapped in invisible lines of magnetic force, arcing from one region to another like rubber bands stretched around a sphere. Most of the time, these field lines loop back into the sun, creating closed structures that trap the superheated plasma of the solar atmosphere and keep it contained. The sun's corona, that outer atmosphere extending millions of miles into space, glows brilliantly in ultraviolet wavelengths because this trapped plasma is heated to temperatures that dwarf the surface below. But sometimes, in certain regions, those magnetic field lines don't loop closed, they open. They stretch outward into space like fingers reaching into the void, and when that happens, the plasma that was contained suddenly has an escape route. A coronal hole is not a physical gap in the sun's surface. It's a region where the magnetic architecture has fundamentally changed, where the structure that normally holds everything in place has released its grip, allowing a continuous high-speed stream of solar wind to pour directly into the solar system, with nothing to slow it down, nothing to deflect it, nothing standing between that cosmic river and whatever happens to be in its path. To understand why this matters, you need to grasp something counterintuitive about the sun's atmosphere. The visible surface you see, that bright disk in the sky called the photosphere, sits at roughly 10,000 degrees, but above that surface, in the corona, temperatures skyrocket to millions of degrees. This seems impossible. How can the atmosphere be hundreds of times hotter than the surface generating it? The answer lies in those magnetic field lines, twisting and reconnecting and snapping, releasing tremendous energy that heats the surrounding plasma to extraordinary temperatures. In normal regions of the corona, that million-degree plasma glows intensely in ultraviolet and X-ray wavelengths, trapped by closed magnetic loops. But in a coronal hole, the field lines are open, the plasma escapes. What remains is cooler, less dense, and far dimmer. When our telescopes observe the sun in ultraviolet light, coronal holes appear as vast dark regions, patches of shadow against the blazing face of our star, like wounds that have opened and are bleeding solar wind directly into space. The coronal hole facing Earth right now is what scientists call a trans-equatorial coronal hole, and that positioning is critical to understanding why this particular opening matters more than most. Coronal holes are not rare. The Sun develops them regularly throughout its 11-year activity cycle. During solar minimum, when the Sun is quiet and relatively calm, large coronal holes appear near the poles and can persist for months or even years. But those polar holes point their high-speed wind streams up and down relative to the plane of the solar system, mostly missing Earth as we orbit along the Sun's equator. A trans-equatorial coronal hole is different. It stretches from the northern hemisphere, cuts directly through the solar equator, and extends into the southern hemisphere. It's aligned with the plane of Earth's orbit, and when it rotates to face our planet, we're staring directly down the stream, like standing in front of a fire hose instead of off to the side. The numbers are staggering in a way that's difficult to comprehend. This particular coronal hole spans hundreds of thousands of miles across the Sun's surface. If you could somehow place Earth on the Sun and slide it into that dark region, you could fit dozens of our planets within the opening. And from that breach, solar wind pours out at speeds approaching 500 miles per second, over 1,800,000 miles per hour, fast enough to cross the vast distance between the Sun and Earth in just a few days. Think about what that means. A stream of electrically charged particles, protons and electrons torn from the Sun's atmosphere, racing across space faster than anything humans have ever built, carrying the Sun's magnetic field frozen into the flow, aimed directly at the only planet in the solar system with a technological civilization that depends on satellites and power grids and global communication networks. That's what our magnetosphere is facing right now. That's the cosmic weather event unfolding while you go about your daily routine, unaware that invisible forces are colliding in the space around our planet. But here's what makes this situation genuinely significant beyond just the size and speed of the solar wind. We're not supposed to be seeing coronal holes like this right now. The Sun follows a roughly 11-year cycle of activity, oscillating between quiet periods called solar minimum and active periods called solar maximum. During solar minimum, the Sun's magnetic field is simple and well organized. Polar coronal holes dominate. Sunspots are rare. Solar flares are infrequent. The Sun is at its calmest. As the cycle progresses toward solar maximum, the magnetic field becomes increasingly complex and chaotic. Sunspots proliferate across the surface. Solar flares erupt regularly. Coronal mass ejections blast billion-ton clouds of plasma into space. The corona becomes a tangled mess of magnetic structures competing and reconnecting and exploding. And during solar maximum, those large polar coronal holes typically shrink or disappear entirely, replaced by more dynamic magnetic configurations. Trans-equatorial coronal holes of this size usually appear during the descending phase of the solar cycle, after the maximum has passed and the Sun begins calming down on its way to the next minimum. They're a sign that the magnetic field is transitioning back toward a simpler structure. But we're supposed to be near solar maximum right now, deep in the active phase of solar cycle 25, and yet this massive trans-equatorial coronal hole has appeared, persisting for weeks as the Sun rotates, repeatedly sweeping Earth with its high-speed wind stream. That's unusual. That suggests the Sun's magnetic behavior during this cycle is not following the textbook pattern that scientists predicted. Some researchers now speculate that we might be experiencing a double-peaked maximum, where solar activity rises to one peak, declines slightly, then rises again to a second peak before finally descending toward the next minimum. Others suggest that solar cycle 25 is simply more magnetically complex than the simplified models anticipated. Either way, the presence of this coronal hole right now, at this phase of the cycle, in this position, with this size and persistence, represents something that catches attention because it's highly unusual at this stage of the cycle and has been sustained. Scientists monitor these structures using a fleet of spacecraft positioned between the Sun and Earth, observing the corona in wavelengths of light invisible to human eyes. The images they capture reveal the coronal hole as a vast dark void, a region where the normal glow of the solar atmosphere has fled into space. Around the edges you can sometimes see bright streamers, magnetic field lines still trying to contain plasma before they too break open. The interior is starkly different, dark and depleted, a region where the solar wind has won its battle against magnetic confinement and now flows freely toward whatever lies downstream. And right now, we lie downstream. When that wind reaches Earth, it doesn't strike the surface directly. We're protected by the magnetosphere, an invisible magnetic bubble generated deep within our planet's core and extending tens of thousands of miles into space. This shield deflects most of the solar wind around us, channeling it into a long tail on the night side of Earth. But the interaction is not gentle or passive. When high-speed solar wind from a coronal hole slams into the magnetosphere, it compresses our magnetic field, injects tremendous energy into the system, and triggers what we call geomagnetic storms. These storms manifest in several ways. The most beautiful consequence is the aurora, those shimmering curtains of green and red and purple light that appear near the poles as charged particles funnel down magnetic field lines and collide with our atmosphere, exciting oxygen and nitrogen atoms until they glow. During strong geomagnetic storms driven by coronal hole wind, auroras can appear far south of their usual territories, visible from latitudes that normally never witness them. But the consequences extend far beyond pretty lights in the sky. Satellites orbiting Earth experience increased drag as the upper atmosphere swells with injected energy, expanding outward and increasing density at orbital altitudes. GPS signals degrade as the ionosphere, that electrically charged layer of the atmosphere, becomes disturbed and unpredictable. High-frequency radio communications black out, particularly over polar routes where aircraft depend on them to stay in contact with ground control. And in extreme cases, geomagnetically induced currents flow through long-distance power transmission lines, stressing transformers, and potentially causing blackouts that can cascade across entire regions. This is the reality of living on a planet orbiting an active star. The sun doesn't just provide the light and warmth that makes life possible. It breathes, it exhales, and when a coronal hole opens and points at us, we stand in the path of that cosmic breath, protected only by a magnetic field generated deep beneath our feet by churning currents of molten iron in the outer core. So when you hear about a coronal hole large enough to swallow dozens of Earths aimed directly at our planet, releasing solar wind at over 1,000,000 miles per hour, the question that naturally arises in any reasonable mind is simple and stark. Can it destroy Earth? Can this opening in the sun, this breach in its magnetic atmosphere, actually end everything we've built, strip away our protection, reduce our technological civilization to darkness and silence? The short answer, the one that prevents panic and keeps perspective, is no. But the nuanced answer, the one that takes into account our modern dependencies and the lessons we've learned from history, is far more interesting and far more relevant to your daily life than a simple reassurance. Because while the planet itself is not in danger, while Earth has survived billions of years of solar wind bombardment and will continue to survive long after humans are gone, the infrastructure we've built over the past century exists in a state of vulnerability that most people never consider until something breaks. And understanding that vulnerability, understanding what the sun is capable of when it really decides to remind us who's in charge, requires looking back at an event that happened more than a century and a half ago, during an era when humanity had barely begun to harness electricity, an event that if repeated today would reshape modern civilization overnight. September 1st, 1859. A British astronomer named Richard Carrington was doing what he did most clear days, observing the sun through his telescope, carefully drawing the sunspots he saw onto paper. This was before electronic cameras, before satellites, before any of the technology we take for granted. Solar observation meant patient, meticulous hand-drawn records of what the sun looked like day after day. And then, as Carrington watched through his telescope, something extraordinary happened. He saw a bright flash erupt from a sunspot group, a sudden, brilliant white light that lasted about 5 minutes before fading. He had just witnessed, without fully understanding what he was seeing, one of the most powerful solar flares ever recorded in human history. The energy from that flare raced across space at the speed of light, reaching Earth in just over 8 minutes. But the flare was only the opening act, the first punch in a 1-2 combination that would demonstrate the sun's true power. What followed was a coronal mass ejection, a billion-ton cloud of magnetized plasma hurled from the sun's atmosphere, traveling much slower than light, but carrying far more physical mass and magnetic energy. That CME reached Earth in roughly 17 hours, extraordinarily fast even by modern standards, suggesting it was moving at exceptional speed, and had been launched directly toward us with almost perfect aim. When it slammed into Earth's magnetosphere, the results were spectacular and terrifying. The Aurora Borealis, normally confined to high latitudes near the Arctic Circle, appeared as far south as the Caribbean. People in Hawaii witnessed it. People in Central America saw shimmering lights in their night sky that had never been seen at those latitudes before and haven't been seen since. The sky lit up with colours so bright that people woke in the middle of the night thinking dawn had arrived. But the Aurora was just the visible symptom of something far more significant happening to Earth's magnetic field. The planet's magnetosphere was being compressed and distorted by the magnetic field embedded in the CME, and massive electric currents were being induced in anything conductive on the surface. In 1859, that meant telegraph wires, the most advanced technology of the era, the Victorian internet connecting cities across continents. Telegraph operators across Europe and North America reported phenomena that seemed impossible. Sparks jumped from their equipment, shocking operators who touched the instruments. Papers caught fire from the induced currents flowing through the wires. Some telegraph systems continued to work even after their batteries were disconnected, powered entirely by the geomagnetic currents induced by the storm itself, messages transmitted using only the energy pouring down from the space weather event. It was a global disruption of the most sophisticated communication technology humanity had developed. And here's the question that should genuinely concern anyone living in the 21st century. What would a Carrington-class event do to our world today? What would happen if a solar storm of that magnitude struck Earth now, in an era where we're not just dependent on telegraph wires, but on satellites and power grids and GPS navigation, and global communication networks and financial systems that exist as electrons flowing through circuits? The answer, based on careful analysis by engineers and space weather scientists, should make you pause and consider just how vulnerable we've made ourselves in the pursuit of technological convenience. Start with the power grid, the electrical infrastructure that powers literally everything in modern life. Power plants generate electricity. Transmission lines carry it across vast distances, sometimes hundreds of miles. Transformers step the voltage up for efficient transmission and down for safe distribution. The entire system operates on a delicate balance of supply and demand, generation and consumption, carefully managed to prevent overloads and cascading failures. When a geomagnetic storm strikes, it induces electric currents in those long-distance transmission lines, currents that don't follow the normal path of power flow, quasi-direct currents that flow unpredictably and can saturate transformers, causing them to overheat and potentially fail. Large transformers, the kind that form the backbone of continental power grids, are not mass-produced items sitting in warehouses ready for immediate replacement. They're custom-built pieces of equipment that can weigh hundreds of tons, cost millions of dollars, and take months or even years to manufacture and install. If a Carrington-class storm took out hundreds of transformers across North America or Europe simultaneously, we wouldn't be looking at a blackout lasting hours or days. We could be facing months or years before full power restoration in some regions, and during that time, everything that depends on electricity stops functioning. Think about what that actually means for daily life. Your refrigerator stops working. Food spoils within days. Grocery stores can't keep products cold. The supply chain that depends on refrigerated transport breaks down. Gas stations can't pump fuel without electricity. Even if you have a generator, your fuel supply is finite. Water treatment plants go offline, meaning no clean water flowing from your taps. Sewage systems fail. Hospitals lose power, and backup generators only function as long as fuel lasts. Communication networks collapse without power to cell towers and data centers. The internet, that nervous system of modern civilization, fragments and fails. Banking systems go offline, and even if you have cash, stores can't process transactions or manage inventory without power. This isn't science fiction or exaggeration. This is a realistic assessment of what prolonged widespread power failure would mean for modern urban populations that depend entirely on continuous electricity for survival. A study by the National Academy of Sciences estimated that a severe solar storm could cause economic damage exceeding $2 trillion in the first year alone, with full recovery taking years. But the economic cost is almost beside the point. The real question is how society functions when the technological systems enabling modern life all fail simultaneously, not for hours but for months. Satellites would face their own catastrophe during a Carrington-level event. We have thousands of satellites in orbit providing GPS navigation, communication services, weather monitoring, Earth observation, and military reconnaissance. During a severe geomagnetic storm, satellites are exposed to intense radiation as particles trapped in the Van Allen belts become energized to extreme levels. Sensitive electronics can be permanently damaged. Satellites can tumble out of control if their attitude control systems fail. Some spacecraft could be lost entirely. GPS satellites are particularly vulnerable, and we depend on GPS for far more than finding directions on your phone. Aviation uses it for precision navigation and landing systems. Shipping uses it for routing cargo across oceans. The financial system uses it for timestamping transactions to prevent fraud. Precision agriculture uses it for automated planting and harvesting. Emergency services use it for dispatch and coordination. Military operations depend on it absolutely for everything from navigation to weapons guidance. If GPS went down globally for an extended period, the cascade effects would ripple through every sector of the economy and every aspect of modern life that depends on precise location and timing. The internet itself, that global communication network we've come to view as essential as electricity, could face severe disruption. Undersea cables, satellite links, fiber optic networks, data centers, all of it depends on electrical power and functioning electronics. A Carrington-class storm could damage infrastructure at multiple points simultaneously, creating outages that aren't easily repaired when the entire system is stressed, and when the specialized equipment needed for repairs is in short supply because everyone needs it at once. We could see regional internet outages lasting days or weeks, and in a world where business, education, government, and personal communication all flow through digital networks, that kind of disruption would paralyze society in ways that are difficult to overstate. Multiple studies have attempted to quantify the risk, and while estimates vary, there's broad consensus that a severe solar storm represents one of the most significant natural threats to modern technological civilization, comparable to or exceeding the potential damage from major earthquakes or hurricanes, but with the added dimension of affecting multiple continents simultaneously. This is why solar physicists and space weather forecasters pay such close attention to major space weather events. This is why understanding what the Sun is doing right now, with that massive coronal hole aimed at Earth, matters beyond academic curiosity or pretty pictures of auroras. Because while the likelihood of a Carrington-level event happening in any given year is low, the likelihood of it happening eventually is essentially certain, and the longer we wait to prepare our infrastructure for that inevitability, the more catastrophic the consequences will be when it finally arrives. But here's the crucial distinction, the piece of information that provides both reassurance and context for understanding the current situation. A coronal hole is not the same threat as a coronal mass ejection. The Carrington event was triggered by an explosive CME, a discrete blast of plasma and magnetic field hurled from the Sun in a single violent eruption. CMEs are like bombs, concentrated releases of energy that can be extraordinarily powerful if conditions align perfectly. A coronal hole, by contrast, produces a sustained stream of high-speed solar wind. It's not an explosion, it's a continuous flow, more like a river than a tidal wave. The geomagnetic storms caused by coronal hole wind are typically less intense than those caused by major CMEs, though they can persist much longer as the coronal hole maintains its structure and repeatedly sweeps Earth with high-speed wind every time the Sun rotates. The risk from a coronal hole isn't a single catastrophic blow that overwhelms our defenses in one devastating moment. It's cumulative stress over days or weeks, the grinding wear on systems designed with certain safety margins that can erode under continuous geomagnetic activity. It's the increased probability that something will fail, not because of one overwhelming impact, but because sustained pressure eventually finds a weak point, like water dripping on stone until it finally cracks through. And this is where the current situation becomes genuinely significant beyond just its unusual timing in the solar cycle. The coronal hole facing Earth right now is enormous, positioned perfectly to send its wind directly at us, and it's persisting as the Sun rotates, meaning we're not dealing with a single event, but a sustained campaign of space weather that could extend for weeks. Moreover, we're near solar maximum, which means other magnetic structures on the Sun's surface could produce additional space weather events, including CMEs, that might arrive while the coronal hole wind is already battering our magnetosphere. When a CME arrives during a period of elevated geomagnetic activity from a coronal hole, the combined effect can be significantly worse than either event alone, like being hit by a wave while you're already off balance from the last one. This is the scenario that keeps space weather forecasters monitoring their instruments carefully during periods like we're experiencing now, watching for any signs that conditions might escalate from concerning to dangerous. So let me return to our central question with the full context now in place. Can this coronal hole destroy Earth? Can it shatter the planet, strip away our atmosphere, extinguish life in some cosmic cataclysm? No, absolutely not. Earth has survived billions of years of solar wind bombardment. The planet's magnetic field, generated deep in the core by convective currents of molten iron, has protected the atmosphere and surface from direct solar wind impact since before complex life even existed. The geological record shows evidence of extreme solar events in the distant past, storms that make even the Carrington event look modest. and life persisted through all of it, the planet will be fine, the biosphere will continue. But can this coronal hole, combined with the elevated solar activity during this phase of the cycle, produce space weather events that damage our technological infrastructure, disrupt critical systems, cause economic harm, and remind us in the starkest possible terms that we've built a civilization exquisitely vulnerable to the moods of our star? Yes, without question. And that's not fear-mongering or exaggeration. That's an honest assessment based on historical precedent, current solar conditions, and our understanding of how geomagnetic storms affect the technologies modern life depends on absolutely. As you're watching this video, a network of spacecraft positioned between the Sun and Earth is monitoring that solar wind stream in real time, measuring its speed, its density, its temperature, and critically, the orientation of its magnetic field. These aren't passive observers taking pretty pictures for public relations. They're our early warning system, humanity's sentries standing guard in the space between worlds, providing the advance notice that allows power grid operators, satellite controllers, and airlines to implement protective measures before the storm hits. The primary sentinel is a spacecraft called DSCOVR, positioned at the L1 Lagrange point roughly 1 million miles from Earth toward the Sun. At this location, the gravitational pull of Earth and Sun balance perfectly, allowing the spacecraft to hover in place with minimal fuel. From this vantage point, DSCOVR sits in the solar wind stream approximately 1 hour before it reaches Earth's magnetosphere. That time window is critical. When DSCOVR detects incoming high-speed wind with a specific magnetic field orientation that maximizes energy transfer into Earth's magnetosphere, forecasters at NOAA's Space Weather Prediction Center can issue warnings. 1 hour isn't much time, but it's enough to put critical systems into protective modes, enough to reroute flights away from polar routes where radio communications are vulnerable, enough to prepare for what's coming. And right now, what's coming is a sustained stream of solar wind moving at speeds that exceed normal conditions by a significant margin. Let me put that in perspective without drowning you in numbers. Normal solar wind travels at speeds that seem fast by human standards, but are actually relatively gentle by cosmic standards. The wind from this coronal hole is moving nearly twice that speed, carrying roughly 4 times the kinetic energy. When it hits Earth's magnetosphere, the impact is immediate and sustained. The magnetosphere, that invisible bubble protecting us, compresses under the pressure. The bow shock, that boundary where solar wind first encounters Earth's magnetic field, gets pushed closer to the planet. Energy floods into the system, heating the upper atmosphere, energizing particles trapped in the radiation belts, and triggering the cascade of effects we call a geomagnetic storm. Current conditions, as reported by space weather monitoring agencies around the world, indicate elevated geomagnetic activity that's been persisting for days. The planetary K-index, a measure of magnetic disturbance that runs from 0 to 9, has been fluctuating in the moderate to active range. During quiet periods, the K-index typically sits around 1 or 2. During the recent impact of this coronal hole wind, readings have spiked into the range that indicates active to strong geomagnetic storm conditions, not quite at the extreme levels that represent the most severe category, but persistent and elevated enough to stress systems and create visible effects. The most dramatic visible effect has been Aurora reports surging from observers at high latitudes and even some mid-latitude locations. The Aurora oval, that ring around the magnetic poles where northern and southern lights normally appear, has expanded significantly. People in northern Europe have reported seeing green curtains shimmering across their night sky. Observers in Canada and the northern United States have witnessed displays that are rare for their latitude. Social media has filled with photographs of the aurora, each one a beautiful visible reminder that energy from the sun is pouring into Earth's magnetosphere, channeling down magnetic field lines, and colliding with our atmosphere to create light. For many people, seeing an aurora is a bucket list experience, something rare and magical. For space weather scientists, it's confirmation that the system is under stress, that the protective magnetic bubble surrounding our planet is being compressed and disturbed by forces streaming from that opening in the sun. Satellite operators have reported increased atmospheric drag on spacecraft in low Earth orbit, exactly what you'd expect when the upper atmosphere heats and expands during geomagnetic activity. This creates real operational challenges. Satellites must use precious fuel reserves to boost themselves back to proper altitude, and if storms persist, fuel can become a limiting factor in a satellite's lifespan. GPS accuracy has shown minor degradations during the strongest periods of activity. The ionosphere, that electrically charged layer of the atmosphere that GPS signals must pass through, becomes chaotic during geomagnetic storms. What's normally a predictable delay becomes unpredictable, and positioning accuracy suffers. For casual users checking their phone for directions, the degradation might go unnoticed. For precision applications in aviation, surveying, or automated systems, it's a measurable impact that requires attention. Airlines flying transpolar routes, those great circle paths between North America and Asia that pass near the North Pole, have had to make adjustments during the most active periods. High-frequency radio communications, which these flights depend on to stay in contact with air traffic control, black out when the ionosphere becomes disturbed. When that happens, flights must reroute to lower latitudes where alternative communication methods work, adding time and fuel costs to the journey. Power grid operators in high-latitude regions, places like Scandinavia and northern Canada, where geomagnetically induced currents are strongest, have been monitoring their systems closely. Currents have been detected in transmission lines, exactly as predicted when geomagnetic activity elevates. So far, these currents have remained within the range that systems were designed to handle, but the monitoring continues because conditions can change rapidly if the solar wind speed increases further, or if the magnetic field orientation shifts to become more geoeffective. This is what it looks like to live through an active solar period, with a major coronal hole facing Earth. It's not apocalyptic scenes of collapsing infrastructure and societal breakdown. It's a sustained test of our technological systems, a period of elevated risk where the margins of safety narrow and operators pay closer attention because they know the sun is in a mood that demands respect. And here's what makes this situation particularly noteworthy, from a scientific perspective beyond just the immediate impacts. This coronal hole appeared and achieved this size during a phase of the solar cycle when such features are less common than they would be during other phases. The sun follows an 11-year rhythm of activity that we've been tracking for centuries, ever since astronomers in the 1700s noticed that sunspot numbers weren't random, but followed a predictable pattern. We're currently in solar cycle 25, which began in late 2019. Initial predictions suggested this cycle would be relatively weak, similar to the underwhelming cycle that preceded it. Those predictions turned out to be wrong. By the early 20s, observed sunspot numbers were already exceeding forecasts. Activity ramped up faster than models expected. By late 2024, the sun officially reached solar maximum, according to NOAA and NASA assessments. And the surprises continued. Even after reaching the peak, activity remained elevated. Large sunspot groups appeared regularly. Powerful solar flares erupted. And now, late in 2025, this massive trans-equatorial coronal hole has opened and maintained its structure for weeks. Something that typically happens during the declining phase of the cycle, not near the peak. The sun's magnetic behavior during this cycle is proving more complex than simplified models predicted, suggesting our understanding of solar dynamics still has room for refinement. Some researchers now speculate that solar cycle 25 might exhibit what's called a double maximum, two distinct peaks of activity separated by months or longer, with the current coronal hole possibly marking a transition phase. What this means practically is that we're living through a period of heightened solar activity that could persist for years rather than months. More geomagnetic storms, more auroras, more stress on satellites and power grids, more reasons to pay attention to space weather forecasts, and critically, more opportunities for truly severe space weather events to occur if conditions align in the wrong way at the wrong time. Because while this coronal hole is producing sustained moderate impacts, the real danger during solar maximum comes from the explosive events, the powerful solar flares and fast coronal mass ejections that can erupt with little warning and arrive at Earth with devastating potential if their magnetic field happens to be oriented perfectly for maximum energy transfer. The combination of sustained coronal hole activity, plus the ever-present possibility of a major CME erupting from one of the active regions dotting the sun's surface, creates a compound risk scenario where our technological infrastructure faces pressure from multiple directions. And this brings us to an important piece of the puzzle that we haven't fully explored yet, the shield that protects us, and whether that shield is as robust as we need it to be. Deep beneath your feet, roughly 1,800 miles below the surface where you're standing or sitting right now, something remarkable is happening that you never think about, but depend on absolutely. Liquid iron churns in massive convective currents, driven by heat escaping from Earth's solid inner core. This molten metal ocean is electrically conductive, and as it flows and swirls driven by the planet's rotation and thermal gradients, it generates electric currents. Those currents produce magnetic fields, and those magnetic fields combine and reinforce each other to create the single most important invisible structure protecting life on this planet, the magnetosphere. This is not a static, unchanging barrier, it's a dynamic living system, constantly fluctuating in response to changes deep within Earth and to the solar wind battering it from outside. And it's been operating continuously for over 3 billion years, long before humans existed, long before complex life evolved, protecting our atmosphere from being stripped away by solar wind, the way Mars lost most of its atmosphere when its magnetic field died billions of years ago. The magnetosphere extends tens of thousands of miles into space, far beyond the orbits of any satellites, far beyond where the atmosphere thins to nothing. On the side facing the Sun, it's compressed by the relentless pressure of solar wind into a bow shock, a sharp boundary where particles streaming from the Sun encounter Earth's magnetic field and are deflected around us. On the night side, the magnetosphere stretches into a long tail, streaming away from the Sun, extending far beyond. The Moon's orbit. Inside this magnetic bubble are the Van Allen radiation belts, two donut-shaped regions filled with charged particles trapped by Earth's magnetic field, spiraling along field lines, bouncing between northern and southern magnetic poles. This system has shielded Earth through solar cycles far more active than anything modern humans have directly experienced. It survived massive solar storms in the distant past, events we can detect now only through their signatures preserved in ice cores from Greenland and Antarctica, isotope ratios in tree rings, magnetic minerals in lake sediments, events that would have been catastrophic for modern technology, but which the biosphere weathered without mass extinctions. The magnetosphere works. It's proven itself over geological timescales, but it's not unchanging, and there are trends in the data that deserve honest discussion, not because they suggest imminent catastrophe, but because understanding our shield's behaviour matters when we're asking whether the Sun can threaten Earth. First, the magnetic poles wander. The North Magnetic Pole, the point where Earth's magnetic field lines point straight down into the planet, does not sit at the geographic North Pole. It's currently located in the Arctic Ocean, and it's been moving from Canadian territory towards Siberia at a rate that has accelerated over recent decades. A century ago, the pole drifted at roughly 10 miles per year. Now it's moving at roughly 30 miles per year or more. The South Magnetic Pole similarly wanders off the coast of Antarctica. These movements reflect changes in the flow patterns of molten iron deep in the core. The magnetic field is generated by a complex dynamo process that's not perfectly stable. Currents shift, flow patterns evolve, and the resulting magnetic field adjusts accordingly. This pole wandering is completely normal. It's been happening throughout Earth's history. What's more dramatic is that occasionally, over timescales of hundreds of thousands of years, the magnetic field completely reverses. North becomes south, south becomes north, in what's called a geomagnetic reversal. The geological record preserves clear evidence of these reversals in volcanic rocks that recorded the magnetic field orientation when they cooled and solidified. The last reversal happened roughly 780,000 years ago. On average, reversals occur every few 100,000 years, though the timing is highly irregular and unpredictable. By that measure, we're statistically overdue for another reversal, but overdue in geological terms means very little. It could happen soon, or not for tens of thousands of years. During a reversal, which takes thousands of years to complete, the magnetic field weakens significantly and becomes chaotic, with multiple north and south poles appearing and disappearing at various locations across the planet's surface. During these transition periods, Earth's protection from solar wind and cosmic rays is reduced, though not eliminated entirely. The field doesn't vanish, it just becomes less organized and weaker. There's no evidence that past magnetic reversals caused mass extinctions. Life survived them, adapted, continued. But we've never had a technological civilization dependent on satellites and power grids and precise navigation during a reversal, so we genuinely don't know what the space weather impacts would be on modern infrastructure during such an event. Setting aside the very long timescale of reversals, there's another trend that's more immediately relevant. The magnetic field is weakening. Measurements over the past few centuries show that Earth's magnetic field strength has declined by roughly 10 to 15%. This isn't necessarily alarming on its own, because magnetic field strength fluctuates naturally over time, but it's a measurable trend that scientists monitor with instruments on the ground and satellites in orbit. In one region in particular, the weakening is pronounced. It's called the South Atlantic Anomaly, a vast area stretching from South America across the Atlantic Ocean towards southern Africa, where the magnetic field is significantly weaker than the global average. In this region, the the inner Van Allen radiation belt dips closer to Earth's surface, meaning satellites passing through the anomaly are exposed to higher doses of radiation than they experience elsewhere in their orbits. The Hubble Space Telescope automatically shuts down its sensitive instruments when passing through the South Atlantic anomaly to avoid damage from energetic particles. The International Space Station implements extra radiation protection protocols for astronauts during transits through the region. Satellites experience higher rates of glitches and malfunctions when traversing this zone. The South Atlantic anomaly has been growing and drifting westward over decades. Some researchers have speculated that it might be an early indicator of a magnetic field reversal beginning, though that remains highly uncertain and debated. So given these trends, the pole wandering and acceleration, the overall field weakening, the South Atlantic anomaly expanding, does this mean Earth's magnetic shield is failing, and we're more vulnerable to solar threats than we used to be? The honest answer is marginally yes in certain respects, but not catastrophically. A weaker magnetic field means the magnetosphere is compressed slightly more by solar wind for a given level of solar activity. It means more solar wind particles can potentially penetrate closer to Earth during geomagnetic storms. It means conditions in space around our planet are somewhat more challenging for satellites than they were centuries ago when the field was stronger. But Earth's magnetic field is not on the verge of collapse. The weakening we've observed is well within the range of normal fluctuations documented over millennia through paleomagnetic studies of rocks and sediments. The South Atlantic anomaly, while significant for spacecraft operations, does not represent a threat to life on the surface or to the magnetosphere's overall protective capability. Even during magnetic field reversals, when the field weakens substantially and becomes disorganized, it doesn't disappear entirely. Earth retains significant protection, and critically, the planet has survived 3 billion years with this magnetic field system operating, through solar cycles when the sun was younger and potentially more active, through periods when cosmic ray bombardment was more intense, through eras when life was far more vulnerable to radiation than it is today, with the ozone layer and atmosphere providing additional shielding. The magnetosphere is not fragile. It's a robust self-sustaining system generated by fundamental planetary processes, the cooling of the core and the rotation of the planet, processes that will continue for billions of years into the future. As long as Earth's interior remains hot and the outer core remains liquid iron in convective motion, the magnetic field will persist. What about the current coronal hole and the geomagnetic storms it's causing? Does the present state of Earth's magnetic field make us more vulnerable to this particular threat? The impact is minimal. The coronal hole wind would have roughly the same effect whether the magnetic field were at current strength or somewhat stronger. The dominant factors determining geomagnetic storm severity are the speed and density of the incoming solar wind and the orientation of its magnetic field relative to Earth's field, not minor variations in the baseline strength of the magnetosphere. So as we pull together all these threads, the nature of coronal holes, the behavior of this particular opening in the Sun, the historical precedent of the Carrington event, the current state of our technology and its vulnerabilities, and the robustness of Earth's magnetic shield, we can finally answer the question that brought you to this video with full context and honesty. Can this giant hole in the Sun destroy Earth? No, it cannot. Not in any literal physical sense. The planet itself is not in danger. Earth's magnetic field, despite the trend scientists monitor, remains fully capable of deflecting solar wind and protecting the surface. The atmosphere is not going to be stripped away. The biosphere is not facing extinction. Life on Earth has weathered far worse from the Sun over billions of years and will continue long after this coronal hole closes and the Sun moves on to its next phase of activity. The planet is safe in every meaningful geological and biological sense. But can this coronal hole, and the broader reality of living under an active star during solar maximum damage, the technological infrastructure we've built over the past century? Can it disrupt satellites, degrade GPS, stress power grids, interfere with communications, and force us to confront the uncomfortable truth that our modern civilization exists in a state of exquisite vulnerability to forces we can monitor and predict but never control? Yes, absolutely and unequivocally. And that's the answer that actually matters for anyone living in the 21st century, because we've spent the last 100 years building a world that depends on technologies the Sun can reach out and touch. We've surrounded ourselves with satellites that orbit in the space environment the Sun controls. We've connected ourselves with power grids that span continents, creating vast conductive networks vulnerable to geomagnetically induced currents during solar storms. We've made ourselves dependent on GPS navigation for everything from finding restaurants to landing aircraft to coordinating financial transactions. We've built a global communication system that runs on satellites and undersea cables and data centers, all of which require continuous electrical power and functioning electronics. And all of it, every single piece of this technological civilization, operates within the sun's sphere of influence, subject to its moods, vulnerable when it decides to remind us that we're not in control. The coronal hole facing Earth right now is not going to end civilization. It's not going to plunge us into a new dark age. But it is producing sustained geomagnetic activity that tests our systems, that finds weak points, that demonstrates in real time what happens when the sun is even moderately active and aimed in our direction. And the critical realization is that this is not even close to the worst the sun is capable of. The Carrington event demonstrated far greater power. Geological evidence suggests even more extreme events in the distant past. And someday, perhaps in our lifetimes, the sun will produce another Carrington-level storm or worse, and when that happens, the resilience of our technological civilization will be tested in ways we can only partially prepare for. We are not helpless observers waiting for cosmic disaster. Over the past several decades, as our dependence on space-vulnerable technology has grown, so too has our capacity to monitor, forecast, and prepare. We have a fleet of spacecraft observing the sun continuously in multiple wavelengths, watching for coronal holes and sunspots and erupting flares and launching coronal mass ejections. We have models that can predict with increasing accuracy when high-speed solar wind will arrive and how severe the resulting geomagnetic activity will be. We have protocols in place for power grid operators to implement protective measures when major storms are forecast. We have satellite operators who can put spacecraft into safe mode during peak radiation periods. We have airlines that reroute flights away from polar regions when radio communications are threatened. All of this represents progress, recognition that space weather is a real and consequential phenomenon that requires attention and resources. But preparation is incomplete and ongoing. Power grids in many regions remain vulnerable to geomagnetically induced currents during extreme events. Satellite constellations continue to grow, without always incorporating the level of radiation hardening that worst-case scenarios would require. GPS remains a single point of failure for countless systems that have no viable backup if the constellation goes offline for extended periods. We're better prepared than we were decades ago, but we're not yet prepared for the worst the sun can throw at us, and the gap between current resilience and what's needed to survive a Carrington-level event or worse remains significant. The coronal hole facing us now will eventually rotate away as the sun turns. The high-speed solar wind stream will sweep past Earth and continue into the outer solar system. Geomagnetic activity will subside. Auroras will retreat to their usual high-latitude territories. Satellites will resume normal operations. Power grid operators will relax their monitoring. And life will return to the baseline routine where most people never think about the sun, except as that bright thing in the sky that provides light and warmth. But in roughly 27 days, if this coronal hole maintains its structure, it will rotate back into an Earth-facing position, and the cycle will repeat. The sun's rotation period means that persistent coronal holes can sweep Earth repeatedly, causing recurring geomagnetic activity every solar rotation. Some coronal holes last for months, appearing and reappearing in satellite observations like cosmic clockwork. Each time the hole faces Earth, the high-speed wind returns, the magnetosphere gets compressed, auroras appear, satellites experience stress, and the technological systems we depend on face another test. This is the rhythm of living under an active star, and it's a rhythm we need to understand and respect as we build our future, because that future includes more satellites, more dependence on space-based infrastructure, more integration of GPS into critical systems, more reliance on the assumption that the space environment will remain benign enough for our technology to function without catastrophic failures. There will be more coronal holes in the years ahead. Solar cycle 25 will eventually wind down and transition towards solar minimum, but cycle 26 will follow, and the sun will continue its 11-year heartbeat for billions of years into the future, long after humans are gone, long after every satellite we've launched has fallen from orbit and burned up in the atmosphere. Our challenge is not to stop the sun from being active, we can't, but to build a technological civilization that can coexist with that activity, that can absorb the impacts of geomagnetic storms without cascading failures, that can recover quickly when systems do fail, and that maintains backup capabilities for critical functions when space weather makes primary systems unreliable. Understanding space weather has to become part of basic scientific literacy for anyone living in a modern society, the same way understanding weather on Earth is essential for anyone planning outdoor activities or making travel arrangements. You check the weather forecast before planning a picnic. In the future, power grid operators and satellite companies and airlines will check the space weather forecast with the same routine diligence, because ignoring what the sun is doing is no longer an option. When so much depends on systems the sun can disrupt, there's something profound and humbling about realizing that we live on a planet orbiting a star that's alive in its own way, dynamic and active, following rhythms and processes that dwarf human timescales and human power. We've built extraordinary things over the past century. We've created technologies that would seem like magic to our ancestors. We've connected the entire planet in networks of information and power. We've extended our reach into space with satellites and probes exploring the solar system. And yet a simple opening in the sun's magnetic field, a structure with no consciousness and no intent, can reach across 93 million miles of space and touch what we've built, reminding us that we're still small creatures on a small world, living in a dynamic universe that doesn't revolve around our needs or our convenience. But there's also something empowering about understanding this reality. Knowledge is protection. Awareness enables preparation. By watching the sun, by studying its behavior, by developing the science of space weather forecasting, by building resilience into our infrastructure, we're learning to be a species that can thrive in the space environment that surrounds us. We're adapting to the reality that our star is active and will remain so for billions of years. We're not helpless victims. We're a technological civilization learning to operate in a cosmos that includes both wonder and danger, beauty and threat, in measures that demand respect and preparation. The giant hole in the sun will not destroy Earth. The planet has survived for over 4 billion years, through solar storms far more powerful than anything we've directly measured, through magnetic field reversals and asteroid impacts and mass extinctions, and it will continue to survive long after humans are gone. Life will persist. The oceans will still flow. The continents will still drift on their tectonic plates. The magnetosphere will still deflect solar wind. Earth doesn't need our protection from the sun, but our civilization, fragile and impressive in equal measure, built on technologies that have existed for merely decades, in a universe that measures time in billions of years, that does need our attention and our preparation. And the coronal hole facing us right now is providing exactly the kind of real-world test that helps us understand where our vulnerabilities lie and what we need to do to address them before the sun produces something far more powerful than a sustained wind stream from an open magnetic structure. Someday the sun will erupt with a Carrington-level coronal mass ejection, or worse, and when that day comes, our survival as a technological species will depend on the preparations we're making now, the lessons we're learning from events like this current coronal hole, and the wisdom to respect the power of the star that gives us life. Thank you for staying with me through this exploration. If you've made it this far, you now understand something that most people never consider, that we live in a dynamic relationship with our star, that the sun is not just a passive provider of light and warmth, but an active force that shapes the space environment around Earth, and that our modern way of life exists in a state of vulnerability that requires ongoing attention and preparation. The next time you see auroras in the news or hear about GPS disruptions or read about solar storms affecting power grids, you'll understand the context, the science, the history, and the stakes. You'll know that it's not random, that it's not a conspiracy or a system failure, but the sun doing what the sun has always done, being an active star with magnetic personality and occasional outbursts, and our technology encountering the limits of operating in that environment. Stay curious about the cosmos, stay aware of space weather, and remember that living on a planet orbiting an active star is both a privilege and a responsibility, offering us beauty in the form of auroras and sunlight, and demanding from us the wisdom to build our civilization with resilience against the forces that stream from that brilliant point of light 93 million miles away.